Imagine being able to see through solid rock, to peer inside a fossil without ever cracking it open. This isn't science fiction, it's the cutting-edge reality of modern paleontology. Advanced imaging techniques are revolutionizing how we study the past. For centuries, paleontologists had to rely on what they could see with their naked eyes. They carefully chipped away at rocks, hoping to reveal fossils within. But now, we have tools that let us look inside fossils without damaging them. These new techniques are like giving paleontologists superpowers. They can now see through rock, peer inside bones, and even detect the colors of creatures that lived millions of years ago. From CT scans to 3D modeling, from synchrotron radiation to laser scanning, we'll uncover the tools that are helping us unlock the secrets of the past. Get ready for a journey through time, as we see how modern technology is helping us understand ancient life like never before. CT scanning, or computed tomography, is like giving paleontologists X-ray vision. It allows them to see inside fossils without ever picking up a chisel. The process works much like medical CT scans used in hospitals. A series of X-ray images are taken from different angles. These are then combined by a computer to create a detailed three-dimensional image of the inside of the fossil. This technique has been a game-changer in paleontology. In the past, if scientists wanted to study the inside of a fossil, they often had to cut it open. But with CT scanning, they can now examine the internal structure of fossils without harming them. CT scanning has revealed amazing details about ancient life. For example, it's shown us the inner ear structures of dinosaurs, giving clues about how they moved and balanced. It's allowed us to see the brain cases of early mammals, helping us understand how mammal brains evolved. It's opening up new possibilities for collaboration and preservation in paleontology. 3D modeling is like digital sculpting for paleontologists. It turns CT scan data into lifelike models of ancient creatures. These are fully three-dimensional and can be examined from every angle. This has transformed how we visualize extinct animals. We can now create accurate representations based on fossil data. Synchrotron radiation might sound like something from a science fiction movie, but it's actually a powerful tool for studying fossils. A synchrotron is a type of particle accelerator that produces extremely bright X-rays. These X-rays are much more powerful than those used in conventional CT scans. They can reveal details that other techniques miss. The process works by firing these intense X-rays at a fossil. As the X-rays pass through the specimen, they interact with different materials in different ways. This allows scientists to create incredibly detailed images of the fossil's internal structure. One of the most exciting applications of synchrotron radiation is in studying fossils preserved in amber. With synchrotron radiation, scientists can see inside these amber fossils without cutting them open. They've discovered perfectly preserved insects from millions of years ago, complete with internal organs and even the last meal in their stomachs. Synchrotron radiation has also been used to study larger fossils, revealing the structure of dinosaur eggs and the growth patterns of ancient trees. Section 5: X-ray fluorescence, revealing ancient colors. Have you ever wondered what color dinosaurs really were? For a long time, this seemed like a question we could never answer. Fossils don't preserve color after all, or do they? Thanks to a technique called X-ray fluorescence, we're now able to detect traces of pigments in some fossils. This is giving us our first real glimpses of the colors of ancient life. X-ray fluorescence works by bombarding a sample with X-rays. This causes the atoms in the sample to emit their own X-rays. Different elements emit different wavelengths of X-rays. By analyzing these, scientists can determine what elements are present in a fossil. Some of these elements are associated with specific pigments. For example, copper is often found in black pigments. This technique has led to some stunning discoveries, revealing patterns and colors in ancient feathers and scales. Section 6: Laser scanning, capturing minute surface details. Laser scanning is like taking the world's most detailed photograph, but instead of capturing light, it captures shape. This technique uses lasers to measure the distance to different points on an object's surface. By taking millions of these measurements, it creates an incredibly detailed three-dimensional map of the object's shape. In paleontology, laser scanning is used to capture the finest details of fossils. It can record surface textures that are too small to see with the naked eye. This is particularly useful for studying things like fossil footprints, teeth marks, or the texture of dinosaur skin impressions. One of the great advantages of laser scanning is its speed and portability. Unlike CT scanning, which often requires fossils to be taken to specialized facilities, laser scanning can be done in the field. This means that large or fragile fossils that can't be moved can still be studied in great detail. Section 7. Photogrammetry. Creating 3D models from photographs. Photogrammetry is like building a three-dimensional puzzle from two-dimensional pieces. It's a technique that uses regular photographs to create three-dimensional models. The process involves taking many overlapping photos of an object from different angles. Special software then analyzes these photos to figure out the three-dimensional shape of the object. This technique is particularly useful in paleontology because it's simple and inexpensive. All you need is a good camera and the right software. This means that even small museums or individual researchers can create detailed three-dimensional models of their specimens. Photogrammetry is especially valuable for studying large fossils or entire dig sites. It can be used to create three-dimensional models of entire dinosaur skeletons, or to map out the positions of fossils in a quarry. This helps paleontologists understand how fossils are positioned relative to each other, which can give clues about ancient environments or how animals died. Section 8. Micro-CT Scanning, Exploring Tiny Fossils. Micro-CT scanning is like having a microscope with X-ray vision. It's a specialized form of CT scanning that can create three-dimensional images of extremely small objects. While regular CT scans might have a resolution of a millimeter or so, micro-CT can resolve details as small as a few micrometers. That's smaller than the width of a human hair. This technique is revolutionizing the study of tiny fossils. Many important fossils are actually quite small. Things like early mammals, small reptiles, or even single-celled organisms. With micro-CT, scientists can examine these fossils in incredible detail without damaging them. They can see internal structures that would be impossible to study any other way. Micro-CT has led to some amazing discoveries. It's been used to study the brains of early mammals, helping us understand how mammal intelligence evolved. It's revealed the internal structure of ancient plants, showing how they grew and reproduced. T-Rex reimagined through advanced imaging. Advanced imaging techniques have transformed our understanding of Tyrannosaurus rex. CT scans reveal a powerful bite and a flexible skull. The skull could absorb biting forces without breaking. 3D modeling shows T-Rex was bulkier and more muscular. X-ray studies suggest camouflage patterns. These insights reshape our understanding of T-Rex. Section 10. The Future of Paleontology, Digital Museums and Virtual Reality. As we look to the future, it's clear that digital technology will play an increasingly important role in paleontology. One exciting development is the concept of digital museums. These are online repositories of three-dimensional fossil models that anyone can access from anywhere in the world. They're democratizing access to fossil collections, allowing researchers and the public alike to study specimens that might otherwise be off-limits. Digital museums are more than just collections of three-dimensional models. They can include detailed information about each specimen, including where it was found, how old it is, and what it tells us about ancient life. Virtual reality, or VR, is another technology that's set to transform paleontology. VR can allow people to experience prehistoric environments in immersive 3 dimensions. Imagine walking among dinosaurs or exploring an ancient reef teeming with bizarre creatures. These experiences can make paleontology more engaging and accessible to the public. Section 11. Conclusion. A new era of discovery in paleontology. As we've seen, advanced imaging techniques are ushering in a new era of discovery in paleontology. They're allowing us to see fossils in ways that were once unimaginable. From peering inside solid rock to recreating the colors of long-extinct creatures, these tools are revolutionizing our understanding of ancient life. But perhaps the most exciting aspect of these new technologies is that they're constantly evolving. Each year brings new advances, new techniques, and new possibilities. As computing power increases and imaging technology improves, we can expect even more detailed and revealing studies of fossils in the future. These advances aren't just changing how scientists work, they're also transforming how the public engages with paleontology. Through three-dimensional printing, virtual reality, and online repositories of fossil data, people around the world can now interact with the prehistoric past in ways that were once the exclusive domain of museum curators and researchers.